Okay, so the next concept that, and probably the last concept that we have in this review is the concept of functions. So, and this is important. So basically a function is basically nothing but a special type of relation. Basically it's a function, you can say that a function is nothing but a special type of relation. Meaning that if there are certain conditions imposed on a relation, that relation can be called a function. That relation can be called a function. So what that means is that we said that, for example, we had for example this set over here A and this set over here B, and we had all of these elements in here, and we had all of these elements in here, and then for example we said that basically we could calculate the Cartesian product of the two sets. That would be a set of elements, a set of ordered pairs. From those ordered pairs, if I take all or some of the elements and basically call it, for example, something like a set R, that would be called a relation. Meaning that, for example, suppose that I'm not taking all of the ordered pairs in here, just a couple of them. So for example, something like this, and then I have, for example, something like this and something like this. Then of course this is basically called a relation R from A to B, right? This is called a relation R from A to B. So we have no problem with that. Based on our definition, everything is correct. We have no problem with that. But now basically the same concept that we have here that we call the relation, suppose that for some valid reasons I put some conditions on these relations, meaning that I'm going to say that, for example, let's say that I have these two sets over here, A and B, and there is a relation defined on these two sets. There is a relation defined on these two sets. For example, the relation is basically graphically looks something like this. Meaning that every member of the set A has been mapped to some element in the set B. Now this is just some arbitrary thing that I'm saying here. I'm not defining anything as a function or anything like that. You can see that over here, for example, this element has been mapped twice. To two different elements. These elements have been mapped to two different elements. This element has been mapped to nothing, right? So now I'm suppose that I say that, okay, so I don't want this to be so untidy. I want to tidy things up. So I want it, for example, I want to say that basically every element that I can find in here it has to be mapped to some element in the second set, for example, in the codomain, for example. And I'm going to say that, for example, none of these two elements, for example, something like this situation where one single element has been mapped to two different elements, I'm not going to accept that, because this is going to create problems for me. I'm not accepting that. So as you can see, every element here has been mapped to a distinct element in the codomain. And moreover, nothing is left alone here. For example, all of the elements here have been mapped to some element in the codomain. And basically, having all of these conditions in mind, I'm going to call this relation, I'm going to call it a function, f, for example. I'm going to call the function, and that's basically what a function is. It's basically a relation on which some certain conditions have been imposed based on some definitions and based on some requirements. Some specific conditions have been imposed on that relation. And then if that is the case, then you can call that relation a function, right? So basically, for example, you could actually call this a function. There is nothing wrong with this, but this you couldn't actually call a function because for example, this element has been mapped to two different elements here. You don't know what is the value of the value of the function at this point. It's giving you two different outputs, for example. So you don't know which one to take. You don't know if the input is this element here, then it gives you one output here and one output here, and so you would get confused, right? So for the same reason, for example, you cannot call this a function, but this could be called this can actually be called a function. And moreover, what happens is that then there are once those basically conditions are imposed on a relation, and the relation is called a function. What I'm going to do is that it's also possible for me, based on how I relate these elements from the domain to the codomain, or from the domain to the range, based on the way that I basically connect all of these elements together, I can of course define all types of functions. For example, there is a function which is called a one-to-one function. There is a function which is called a one-to-many function. There is a function which is called, there is actually many types of functions. If you come to, for example, on Wikipedia, a few years ago, I found a functions mathematics. I found a very good article here. So you can see that there was a diagram, as far as I can remember, which I cannot see right now. But long story short, there are actually many types of functions, and well, they do different kinds of things based on their definitions. So that's basically the whole story of a function. Now let's do this a little bit more formally and write down a couple of definitions and work with these functions a little bit. And this is just supposed to be just a review, and then in the text that is related to class 12, we will do a better a better analysis of these functions. Okay. Now as a definition, I can say that definition number 5, I can say that the relation f from a set A to a set B is said to be a function if every element of the set A has one and only one image in set B. In other words, a function f is a relation from a non-empty set A to a non-empty set B such that the domain of f is A and no two distinct ordered pairs in F have the same first element, right? So, and then it goes on to say that if F is a function from A to B and the ordered pair A and B belongs to F, then F of A is equal to B. Now we will get to the rest of them. Let me go step by step. We have basically a relation F from a set A to a set B, from a set A to a set B, is said to be a function if every element of set A, if every element of set A has one and only one image in set B, has one and only one image in set B. Okay, so moreover, you could say about functions, you could say in other words, a function f is a relation from a non-empty set A to a non-empty set B such that, so a function is a relation from a non-empty set A to a non-empty set B such that the domain of f is A, that the domain of f is A, is the set A, and no two distinct ordered pairs in F, and no two distinct pairs in F have the same first element. Now we will of course talk about these, what they mean, and if f is a function from A to B, if f is a function from A to B, and the ordered pair A comma B belongs to F, then f of A is equal to B, right? Where B is called the image of A, the image of A under F. Under F, and A is called the pre-image of B under F, and A is called the pre-image of B under F. Okay, so now let's consider these one by one. So basically we said that about this part, we said that basically a relation f from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. If every element of set A has one and only one image in set B. What that means is that, for example, suppose that I have these two sets over here. I have the set A and I have the set B over here, right? So, of course, you know that basically if I have these elements in set A and these elements in set B, so the Cartesian product of A and B would be basically all of these ordered pairs x and x comma y, meaning that you would take this element with this element and take this element with this element. You would take this element with this element, this element with this element, and relative to each of these lines you will have one ordered pair here. So you would have four ordered pairs for this first element, another four ordered pairs for this second element with those four elements there, another four ordered pairs for the third element with these four elements, and another four ordered pairs for this fourth element with the four elements here, which means that the number of these ordered pairs over here would be let's call this, for example, x2 comma y2 all the way up to x of n comma y of n. So then the number of these ordered pairs would be 4 times 4, which is equal to 16 ordered pairs, right? Now, so what, and suppose that basically all of these lines also again exist, and so on and so forth, and so on and so on and so forth, and so on and so forth, and you have basically 16 of these lines. So you have 16 lines here. Now what we said was that we would simply take this, basically take a subset of these elements, meaning that we would basically, I'm not going to take all of these lines here. There is no way to make this bigger, is it? There is a rotate, resize. There is all of these brushes. And then if I go for okay, so let me actually do another one of these. This is going to take me forever and it's not going to work for me. So I'm going to create another for example, something like this. Call it the background color, call it, for example, okay, so now we can work with this. This is actually much better than the other one. Okay, so now what that means is that what that means is that basically I had all of those elements there. So let's say that this is set A and this is set B, and I have all of these elements here, all of these elements here. And normally the Cartesian product of A and B would be this set containing 4 times 4, which is equal to 16 ordered pairs here. 16 ordered pairs here. Now, we said that the Cartesian product, we take a subset of basically the Cartesian product of A and B using some rule and call it R, for example. And R is going to basically contain some ordered pairs. Some ordered pairs, right? Now, let's suppose that, for example, these ordered pairs could be anything, of course. Could be, you could basically connect this one to this one, and this one to this one, and this one to this one, and then you forget about all the other lines that were present here. So we have forgotten about all the 16 lines, we have taken only 4 of them. Now over here we are saying that, and this is of course a relation. So we say that a relation f from a set A to a set B is said to be a function if every element of the set A, meaning that I cannot leave anything out. Meaning that if there was some element over here and if I left that out, then this part which says every element has been neglected. So I'm not supposed to leave anything in here. I have to simply take everything, right? So we said that if every element of the set A, every element, and you can see that now I have taken every element here, and I'm emphasizing this point because it's important, otherwise your relation will not be a function. Okay, so every element of set A has one and only one image in set B. One and only one image, meaning that right now you can see that this element in set A has one and only one image here. This element here in set A has one and only one image here, and so on and so forth. Now what that means is that if this element had this image and also this image, so then of course this would not be a function, because, and so this would not be a function based on the definition. Now, so moreover what we have here is that, in other words, let me move this up here so that you can see what I'm doing. We said that in other words, basically a function is a relation from a non-empty set A to a non-empty set B, right? Such that the domain of f is A, so the domain of f is A, so this is the domain of f, and this relation is basically called f now, right? Instead of writing R, I can simply write f. So the domain of f is A, and is A, and there has to be some and in here. No two distinct pairs in F has the same first element, meaning that, for example, suppose that I have this thing going on in, for example, I have 1, 2, 3, 4, and I have basically 2, 3, 4, and 5, right? And all of these elements are connected in this way, and this is set A and this is set B. So the distinct pairs in F, in this case would be basically 1, 2, and 2, 3, and 3, 4, and 4 comma 5. And of course, please note that even if I had some pair in here, for example 5 comma 4, 5 comma 4 and 4 comma 4 comma 5 would be distinct pairs because the order of the numbers here are different, so they are basically regarded as distinct pairs. But for now, for the sake of simplicity, let's say that this is basically the function that I have. Now over here we said that no two distinct pairs in F have the same first element, meaning no two distinct pairs are supposed to have the first same element, meaning that, for example, if this was the case, then I could write also 4 comma 4, right? Now these are two distinct pairs in F, right? 4 comma 5 and 4 comma 4. These are two distinct pairs in F, and they do have the same first elements, which means that this is not a function, and you're actually not supposed to do this. This is not allowed in functions, right? Which is the same thing as saying that if every element of set A has one and only one image in set B, right? So this is completely clear, and there is nothing wrong with the definition, and completely easy to understand. And we say that if F is a function from A to B, and the order per A comma B belongs to F, then F of A is equal to B, meaning that here I can say that in this situation you can see that basically, for example, the order per A comma B belongs to F, meaning that you can say that, for example, 2 comma 3 in this case belongs to F, right? And so in this case you can say that F of 2 is equal to 3. And in this case basically you can say that 2 is the pre-image of 3 under F, and basically 3 you can call it the image of 2 under F. Okay, so far we have no problems. Now let's move on to the next parts of these definitions. Here we have just a couple of these definitions, and so here we say that basically the function f from A to B is denoted by, so we say that the function f from A to B is denoted by f, and you have to use a colon here, and from A to B. That is the function f from A to B. Looking at the previous examples, we can easily see that the relation in example number 7 is not a function, because for the element 6 has no image, and again the relation in example number 8 is not a, so example number 7 was basically this situation here. Example number 7. So example number 7 was exactly this situation here. So basically we had this set over here, 1, 2, 3, 4, 5, and 6. Right, so we have these elements in here, and you have 1, 2, 3, 4, 5, and 6. And we have this set over here. Now you can call them anything, not important right now. And the mapping is basically done this way. And you can see that this element has not been mapped to anything. It's just hanging in the air. And for the same reason, you cannot call this a function. This is not a function. And moreover, over here we said that if a relation f from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. So every element has to be mapped. If this is not mapped, this is not a function. Moreover, we can say that, for example, in example number 8, we have number 8. And in example number 8, what happens is that we have basically this type of situation in number 8. So in number 8 we have basically these we have these elements, for example 9, 4, and 25, and we have these elements like 5, 3, 2, and 1, and -2, and -3, and -5. We have all of these elements, and the mapping is basically this way. And 4, 2, and 4, -2, and 25, 5, and 25, -5. And so you can see that over here, this element in set A has been mapped to 2 elements in set B, meaning that it has basically 2 images. And so over here, basically we said that if every element of set A has one and only one image, meaning that not more than one image in set B. And so for the same reason, for example, this is not a function. This is not a function. Right? In example number 9, I think, let me see. And the relation in example number 9 is also not a function. So let's see what is wrong with number 9. In example number 9, we have basically now I don't understand. Number 9 is basically not a relation in the first place, but that doesn't matter. In the examples given below, we will see many more relations, some of which are functions and some are not. So now let's get to some examples here. We have a couple of examples. Let's get to them and see what we have over here. So example number 10 is let n be the set of natural numbers and the relation R we defined on n such that R is equal to basically the order pairs x comma y, such that y is equal to 2x and x comma y belong to the set of natural numbers, right? So you can see that the relation R is some relation defined on the set of natural numbers, right? This is some relation defined on the set of natural numbers. And so basically you can imagine that you have the set of basically natural numbers here and the set of natural numbers here, and then R is basically some relation from the set of natural numbers to the set of natural numbers. And you want to know basically what is the domain, the codomain, and the range of this, of R. What is the domain, the codomain, and the range of R, and also if it is a function. And also if the relation is a function, right? So if I write this basically, if x is equal to 1, then if I take x is equal to 1, then of course y is going to be equal to 1/2. Y has to be equal to 1/2, so that 2 times 1 is equal to, y is going to be equal to 2. So if x is equal to 1, then y is equal to 2 times 1, which is equal to 2. So you have all of these ordered pairs, like for example r is equal to 1, 2, and then if x is equal to 2, you will get 4, 2, 4, 3, 6, and basically 4, 8, and so on and so forth. This is R defined on N. Now what's important here is that the domain of R is basically 1, 2, 3, 4, and so on and so forth, all the way up to infinity, which means that the domain is basically 1, 2, 3, all the way up to infinity, which is equal to n, the set of natural numbers. The range of this relation is equal to basically 2, 4, 6, 8, 2, 4, 6, 8, and so on and so forth, which is basically the even natural numbers. Even natural numbers. And of course, the codomain of R is basically the whole set of natural numbers, of course. Is equal to 1, 2, 3, and so on and so forth, which is equal to the set of natural numbers. Now, basically what you can see here is that basically over here, basically I have every natural number every number in the set of natural numbers has been mapped to some element in the set of natural numbers, which means that you have all of the elements in the set of natural numbers here has been covered. There is no element over here which is empty, right? And there is no natural number here in the set of natural numbers that has been mapped to basically to 2 different numbers in this set, in the second set here, which means that this is a function, right? And yes, it is a function. That is your domain, this is your range, and this is your codomain. So basically the domain of R is the set of natural numbers, right? The domain of R is the set of natural numbers n, the codomain is also n, and the range is the set of even natural numbers. And since every natural number n has one and only one image, this relation is a function. It is actually a function, right? So this was question number 10, or example number 10. Example number 11, we have examine each of the following relations given below and state in each case, giving reasons whether it is a function or not. So for example, I have this relation here, which is basically 2, 1, 2, 1, we have 3, 1, and we have 4, 2, and we have 4, 2, right? So you have 2, 1, 3, 1, and 4, 2. You can see that basically in this case, this is basically this situation over here. So you have, let's take this as, for example, set A, and let's take this as set B, for example. Let's say that you have 2, 3, and 4 here. Let's say that you have 2, 3, and 4 here, and you have 1 and 2 here, and 2 is mapped to 1, and 3 is mapped to 1, and 4 is mapped to 2, right? Which means that basically every element has been mapped to some element in here. Okay, so basically, as you can see here in the domain, every element has been mapped to some element, and basically every element has been mapped to some element, meaning that no element has been left empty here, and every element in the domain has its own unique image, meaning that the image of 2 is 1, the image of 3 is 1, and the image of 4 is 2. In other words, you can say that since 2, 3, and 4 are the elements of the domain of R, having their unique images, meaning that well, here basically when we say they have their unique images, what that means is that well, I need to create some situation in order to be able to explain what it means that they have their unique images. But for now, what we will do is that, let's say that since 2, 3, and 4, are the elements of domain of R, are the elements of the domain of R, having their unique images, this relation is a function. This relation is a function. Now, what I'm going to do is that I'm going to create some other situation here, and basically suppose that you have the same elements 2, 3, and 4 here, and you have basically, for example, let's say that you have some element here 1 and 2, and 2 has been mapped to these two elements, right? And for example, 3 has been mapped to this element, and 4 has been mapped to this element, right? Now, as you can see in this situation, 2 is a member of the domain of R, for example, right? 2 is a member of the domain of R, and it has more than one image. And therefore, you cannot call this a function. This is not a function. This is not a function. On the other hand, this is a function for two reasons. Reason number one is that every element of the domain of the function, is basically mapped to some element in the codomain, right? And it doesn't matter if 2 and 3 have been mapped to the same element here. That doesn't matter. That doesn't not make it a function, right? Or that doesn't make it a non-function. So basically, to sum it up, every element over here has been mapped to some element in the codomain, and basically for the same reason you can call this a function. This is a function, but this is not a function, right? So you need to basically what I always do is that basically this kind of situation, you can visualize it. Basically you can visualize it, and you know that this is a function, but this is not a function, meaning that over here you can say that, for example, if this is some, for example, function f, then you can say that f of 2 here is equal to 1. F of 3 here is equal to 1, meaning that you can actually decide what is the image of 2 under f. That's clearly, you can decide that clearly. On the other hand, the image of 3 under f, you can decide that clearly that's equal to 1, right? And suppose that there was some element in here, 5, for example, and it was not basically mapped to anything here. Then in this case, if you wanted to, and this is supposed to be an f. In this case, if you were to say what is the image of 5 under f, you wouldn't know, because it's not mapped to anything. So for the same reason, if this was the case, then this would not be a function. Let's assume that this is not there, right? So basically what that means is that every element that you can find here, it's possible for you, or for example, if you were to ask what is the image of 4 under f, you would simply say it's equal to 2. You can decide that, right? But the problem over here is that if you were to decide what is the image of 2 under, for example, let's call it f, for example, or let's call it r, for example. Well, let's for the moment, let's call it f, for example. And if I were to ask what is f of 2 here, you just simply don't know, because you don't know whether to say 1 or 2. There is no way to decide. Is it 1 or 2? It's just simply not possible. And for the same reason, this cannot be regarded as a function, right? Or you can just simply go with the definition, right? Meaning that each and every element of the domain of the function is supposed to have a unique, basically a unique and one and only one image in the codomain of the function. Now, part 2 of this question is that we have some relation R, which is basically 2, 2 and 2, 4 and 3, 3 and 4, 4, right? So in this case, you have basically 2 is mapped to 2, also mapped to 4. So this is of course not a function. You see, the situation is basically something like this. You have 2 and you have 3 and you have 4 in here, and basically over here you have 2, 4, 3 and 4. So it's 2, 3 and 4 here. Now basically the 2 has been mapped to 2 here, 2 has been mapped to 4 here, 3 has been mapped to 3 here, and 4 has been mapped to 4 here, right? So this is not a problem. I mean, the fact that basically 4 has been mapped to 4 and also 2 has been mapped to 4, that is not a problem. Because you can ask, for example, if I call this f, for example, what is f of 2 here under f, or the image of 2 under f? That's equal to f of 2 is equal to 4. What is the image of 4 under f? F of 4 is equal to 4. So we have no problem there. But then over here we have a problem. Of course, this is also problematic. I will tell you in just a few moments. You see, over here we have this situation where if you were to decide what is f of 2, you couldn't decide. It's either 2 or 4. And this situation cannot exist. A function is supposed to give you a definite output for a definite input. If it gives you 2 outputs for one input, that means that there is something wrong in there. It's not a function, right? So then this is, of course, not a function. And for example, the third basically set this, the third relation here is r is equal to basically 1 comma 2. You have 2 comma 3. You have 3 comma 4. You have 4 comma 5. You have 5 comma 6. You have 6 comma 7. So you see that as far as I'm concerned, every element here, of course, has been mapped to something, and basically there are no 2 ordered pairs which have the same first element, meaning that 1 comma 2, 2 comma 3, 3 comma 4, 4 comma 5, 5 comma 6, 6 comma 7. So it is a function, right? And the reason again is that since every element has one and only one image, then this relation is a function, right? Now, as a definition, and we will talk more about this in depth in the actual course that we are doing after this video. We have, after the review, as a definition number 6. As a definition number 6, I can say that a function which has either R or one of its subsets of R as its range is called a real valued function. So a function which has either R or one of its subsets as its range is called a real valued function. So a real valued function is basically some relation like this. So you have set A and set B here. And of course you know that this basically the elements that you have over here, this is your range. Well, of course, talking loosely about that. This is your range, and if the range is basically if the range of the function is basically the set of real numbers, if this is the set of is the set of real numbers, or a subset of the set of real numbers. So basically, if the range is the set of real numbers, or a subset of that, that set, and of course provided that it's a function in the first place, then the function is called a real valued function. Then the function is called a real valued function. Okay. Now, on the other hand, if the domain is also if the domain of the function is also either R or a subset of R, if the domain of the function is either R, the set of real numbers, or a subset of that, it is called a real function. So if the domain of the function is either R or a subset of that, it is called a real function. Now we will, of course, this idea is not very clear at this point, and we will talk more about this in the videos to come, which are in the videos related to the actual course, not in the review. Here this idea is not very clear. There is no way to understand it properly. Now, to give you some example, to probably understand this idea of real functions and real valued functions, let's say that let n be the set of natural numbers. Of course, n is the set of natural numbers. Now, define a real valued function. Define a real valued function f from n to n by f of x is equal to 2x plus 1. So this is basically, this is the image of x under f, this is the image of x under f, and this is your x, right? So, and using this definition, complete the table below. So for example, the table is something like this. I just want to give you this example. Otherwise, we will talk more about this later. So you have x and y over here, and you have basically 1, and you have 2, and you have 3, all the way up to 7. You have 4, you have 5, you have 6, and 7. Now, if basically we know that f of x is equal to 2x plus 1. That means that wherever if your x is equal to 1, this becomes 2 times 1, which is equal to 2. 2 plus 1 is equal to 3. Then if x is equal to 2, 4 plus 1 is equal to 5. 6 plus 1 is equal to 7. 8 plus 9 is equal to 9. 5, 10, 11, and 13. And you have 12, 13, and 14, 15, right? So this y is actually the image of x under f, and this is your x. So this is the image of x under f, and this is your x. And well, again, it's not clear that it's not really clear why they call this a real valued function, and why that's called a real function, and what's the application of that. We will know more about that in the videos to come. Now we have a couple of other things in this chapter, or in this part, that talks a little bit about functions and so we will do a review of that as well, in case we really need them over there. We will just go through the material quickly. So I'll see you in the next video, and thank you.